Hi everyone, I am presenting an interactive visualization tool for the exploration and analysis of multivariate ocean data. The spatial and temporal visualization of ocean features is critical for many oceanography researchers. The visualization of these ocean data or parameters conveys the inherent trends, patterns, and anomalies in the ocean. Oceanographers therefore often prefer using maps with colorful markers for the visualization and analysis of ocean data. However, there are challenges involved in this area, which include the diverse array of parameters, the ocean parameters such as temperature, salinity, and oxygen content at a wide range of depth and time scales, and the interaction of the multiple parameters needs to be captured in the visualization as well. Researchers utilize approaches that allow them to display several ocean parameters on one plot or chart at the same time to make sense of these complicated observations. This can help the oceanographers to identify patterns and interaction between variables that would not be obvious if each variable is evaluated separately. By visualizing many variables at the same time, it is possible to acquire a more comprehensive understanding of ocean dynamics, as well as how these different patterns or parameters interact with one another. By merging these multiple visualizations, the researcher can acquire a deeper understanding of the intricate relationship between the different ocean characteristics and how they affect marine ecosystems and climate trends. The main goal of this study is to create visual overlays of multivariate ocean data. This will assist oceanographers in better understanding of the different ocean parameters. This paper presents an interactive visualization of multivariate analysis using Python data visualization libraries. Users can benefit from this by better understanding the complex ocean datasets, identifying the patterns and trends in the ocean, and making data-driven decisions. This paper also is contributing to the 3D visualization, in which the study makes use of the octree-based method for data representation, and hence the ray forecasting algorithm is modified to make use of kriging interpolation to achieve the visualization with fewer artifacts. The design method presented for this study includes the architecture, which is divided into 4 layers, namely data layer, data management layer, data rendering layer, and visualization layer. Architecture diagram of the proposed methodology is given here. We can see the data layer, which will accept the different types of data. The data pre-processing and the data format conversion is integrated into the data management layer. Then we have the data rendering layer, which does the CPU and the GPU rendering for 2D and 3D plots respectively, which is connected to the Python interface, wherein which we have a visualization layer which provides a univariate visualization as well as a multivariate visualization. Let us look at the architecture of the first layer, that is the data layer. The framework is designed to work with all commonly used data formats. The datasets mentioned are accessible from the Copernicus site. We use the ocean reanalysis system for data, and we also use the World Ocean Atlas data. Layer in the architecture is the data management layer, which manages data pre-processing, validation, and conversion into the appropriate format. In the data pre-processing step, it ensures that the ocean data is accurate, consistent, and suitable for analysis. We also perform data integration, wherein which the data from different sources or sensors are combined together. The missing data points are addressed using the interpolation method. A format conversion option is also available in the tool, which helps us to solve the problem posed by the different formats. The common data formats which are supported by the proposed tool include netcdf, ASCII, binary and HDF. As we move to the next layer, that is the data rendering layer, the oceanographic data in this layer is rendered to generate 2D and 3D images or animation. The rendering pipeline has a sequence of stages like geometric processing, rasterization, shading, texturing and blending to transform the oceanographic data to a 2D or 3D image or animation. The 2D images are rendered with the support of vector field extraction from data, followed by line rendering and surface rendering. When 3D images are rendered, volume rendering and isosurface rendering schemes are adopted. In the CPU implementation part, the gridded data management scheme is adopted. For instance, in oceanographic data analysis, temperature readings are gathered at different depths and location using sensors or satellites. These data points can be interpolated and rendered using finite difference methods or raycasting algorithm. In CPU rendering, the computer performs calculation in a serial fashion, executing one instruction at a time. In the GPU implementation part, the gridded data is managed using an octree data structure. Octree is a data structure that can be used to represent volumetric data such as ocean temperature, salinity and currents. Octree are tree-based data structures that recursively divide a 3D space into 8 equal sized subspaces or octants. The octree structure allows efficient compression of data by storing only the most significant data values in the parent nodes, while the more detailed values are stored in the child nodes. A sample octree representation of 4 levels is shown over here. Rendering speed in GPU implementation is improved using the sorted sibling traversal. The algorithm starts at the root, and if the ray intersects the root bounds, it will start checking the children. If the child is a non-leaf, we will find the nearest child closest to the ray origin by comparing with the x, y and z planes. To determine which of the parent node's 3 axis planes the ray has collided with, we look for the next closest sibling. The entry point of the beam into the next closest sibling will be revealed by the closest plane that is struck. If no plane is struck, then the ray is headed out of the node and will not hit any other children of the current parent. Else, if the child is a leaf, we can halt the entire process. After the data rendering engine, we have the Python interface. A Python module called Plotly enables us to make interactive web-based visualization. Making interactive maps, scatter plots, line plots and other visualization is possible with Plotly. Python Qt is used as a GUI for interactive visualization, and the Qt framework includes essential elements such as Qt core, Qt GUI and Qt widgets. The next layer in the architecture is the visualization layer, whose objective is to provide univariate and multivariate visualization of the ocean parameters. The univariate visualization techniques available in different methods like color maps, vector plots, contour plots, stick plots, streamline plots and rows plots. In the visualization layer, the oceanographic data is characterized of non-uniform section intervals. Hence, to speed up the raycasting algorithm for volume rendering, appropriate spatial interpolation technique has to be adopted. In our work, the spatial interpolation method chosen is kriging. Kriging uses a linear combination of the observed values in the adjacent nodes of the octree with weights determined by the spatial correlation. Thus, with kriging, the sampling step of raycasting algorithm results in less artifacts. Having discussed the architecture, let us see the results and the associated discussions. The interface of the system has provided options to import data into the framework and provides an interface for data management. The entire tool and the framework is tested on the system of 8 GB RAM and a graphics card of NVIDIA with the specs given over here. The sample screenshots of format conversion is shown over here, wherein you can see the netcdf file is converted into ASCII and also an ASCII file is converted into netcdf format. This is a synopsis of where the different customization options for basic plots are seen. We can see the options given for contour plot, vector plot and color map. Sample examples of basic 2D plots like contour plot, vector plot and color maps are shown over here. Another example of 3D plot with bathymetry data is shown over here. The temperature data is depicted here. An example of the multivariate analysis, that is using the overlay plots, is shown over here. An example over here shows the wind overlaid on temperature anomaly. The temperature anomaly is depicted as color map and the wind data is given as the vector plot. Yet another example of overlay plot wherein which salinity is overlaid on temperature. Let us see the conclusion. This study introduces a novel Python-based interactive tool designed for visualizing multivariate data in both 2D and 3D formats. The tool supports various data formats and allows for single variable visualizations like vector plots and color map as well as multivariate visualization. It processes and refines data using multiple pre-processing techniques and accommodates octree representation and kriging interpolation for improved 3D plots. Overlay plots depicted in the study enable comparison and the identification of patterns, trends and correlations among diverse variables. As a future work, we can try adding real-time data integration and analysis to the tool's capability, which will help us to discover and provide more dynamic and instantaneous insights into ocean conditions.